Hi, this is Chris, and we're taking a look at part B of this bungee jump question. And we're getting into a little bit more of the technical aspects of it. So here it asks, at what instant is there the greatest tension in the cords? And the tension is going to be created by this spring force that we see over here, the Kx value. So your force on a spring is given by Hooke's law, which is F equals negative Kx. And it's really important to appreciate here, the negative doesn't change much in terms of the numerical value, but it just indicates that your spring force is always going to be in opposition to motion. It's a restoring force. And so here, if our spring, if these cords in this case, is going to have a length of, it says that the cords are, let me scroll up a tiny bit, but up here it says the cords are 13 meters long. See where it says 13 meters long? So when they get to 13, anything past that, as it continues in this downward direction, then that means that there's going to be a spring force that's pulling it back towards that equilibrium point. It's trying to get back to equilibrium. So the further that you are from your equilibrium point, the higher the value for x in this equation. X is equal to your displacement from equilibrium. And if x represents your displacement, then to have the greatest tension means that that's going to occur when we have the greatest displacement, when we are stretched as far away from that equilibrium position. And that is going to occur when we are here at the bottom. So once you get to that full 35 meters all the way down here, that spring is pulling back really strongly because it's stretched so far. And that spring force, F equals negative Kx, so the x having a very high magnitude at that point means that basically if you think of a fully stretched spring, as soon as you let it go, so when you get to the bottom of your bungee fall initially, you're going to spring back up really fast, right? And you're going to oscillate back and forth a little bit, and it's going to slow down eventually to where you're just hanging still. But that first spring back up is going to be pretty significant here because that displacement is so large. So that's where we're going to have the greatest tension in the cords. Now for part C, it says, what is the jumper's speed at this instant? Well, let's think. When you jump off of that platform, and you fall, and then you get to this point down here, when you get to that maximum extension, for a split second, just for that brief moment, so you fall, and then you pause, and then you spring back up, right? And your speed at that very moment is going to have a velocity of 0. For that moment, you'll be still, and then that spring will pull you back up at a high rate of speed, but initially you'll be still, and it's going to work the same in the opposite direction, which might be easier to conceptualize. So here, if you were to take a ball and throw it up in the air, it reaches its peak, and then for that split second, it sits still for a moment before it starts coming back down, right? So at the top of a peak or at the bottom of a valley, when you're looking at any sort of projectile motion or oscillation in the case of a spring, when you're going back and forth, it's right at the very ends, maximum extension and maximum compression, to where your speed, your velocity, is going to be 0. Up next, we'll talk about the changing momentum that we see asked about here in part D.